Okay, so hey guys, how's it going? So today I'm going to be going through my lecture on cavity theory, and I have 8 questions to go through in this video. Uh, Within this video, I've included many example problems and worked out calculations. I think that it's an excellent lecture. So with that being said, let's begin. Okay, so problem 1. What is cavity theory? And I'll go ahead and include B. And why do we need it? So suppose we want to measure dose at this location in, let's say, a water phantom. Well, in many instances, what we're using is an ionization chamber to measure the radiation dose. An ionization chamber is essentially a capsule filled with gas, typically air. So suppose we put an ionization chamber at this location right here. Well, what we need now is a formalism to relate the measurement at this location with the ionization chamber here back to the initial starting measurement, as if the ionization chamber was never there in the first place. So essentially, cavity theory, it's determining dose in a medium, as in water, at a location by putting a measuring device. In our case, in many instances, we're using ionization chambers, which is air, and we're relating the dose measured with the device at that location with the device removed. So yeah. Part B. So why do we need cavity theory? Well, essentially there aren't any good radiation measurement devices that measure radiation directly. The closest we have is calorimetry, and that measures a difference. It's a very small difference in temperature. But as you can imagine, you're going to run into many other problems. If it's only measuring a small difference in tiny temperature, there are going to be other problems with that type of measurement device. So moving on to part C, what are the names of the 3 main cavity theories? So we have Bragg-Gray, Spencer-Addix, and Berlin cavity theory. Now, what this is right here is a website that essentially what it does is within these calculations we're going to be using stopping powers, in many instances stopping power ratios, and you typically you're going to be looking up like a stopping power of a material at some particular energy, like 3.889 MeV. And if you're looking up the stopping power in a table, they might only have like 3.5 and 4.0. So you'll have to perform some funny interpolation. But you have to remember that with stopping powers, the interpolation isn't linear, right? So in this case, like at this particular website, you can type in the exact energy and get an exact stopping power. So it's very useful. Okay, so moving on to problem 2. What is the formula to measure dose in a gas cavity? Not the Bragg-Gray formula, not yet. So the formula is measure dose in gas cavity. It's the charge measured over the mass of the gas, which is m, over or multiplied by W over E, which is the average energy to produce an ion pair in gas, in this case. Now for B, what is the formula to relate dose in a medium to dose in gas? It's basically Bragg-Gray, but not quite there yet. So dW denotes the this could be dose in a medium. dg, in our case, dose in the cavity or dose in gas, it's equal to the ratios of the average stopping powers, average collision stopping powers. And I'll show you examples later on how to calculate these. And then C, finally, what is the Bragg-Gray formula? Oh, yeah. So here we go. It's the average mass collision stopping power. So here's the formula for Bragg-Gray. It's the charge measured divided by the mass in gas times W over E, average energy in air to produce an ion pair, and SI over rho, which is with the line on top of S, which is the average mass collision stopping power ratio, right? Where W denotes the wall or medium, and G is the gas or cavity. For D, what are the two conditions to use Bragg-Gray cavity theory? So the first condition is that the cavity must be small as compared to the range of charged particles. The cavity must not perturb the fluence of charged particles in the medium. That's the first condition. The second condition is that the absorbed dose in the cavity is deposited solely by charged particles crossing it. Photon interactions are assumed negligible or negligible. Now for E, do we need charge particle equilibrium for Bragg-Gray? And this is actually a tricky question. So the answer is no. You do not need charge particle equilibrium for Bragg-Gray. But probably what you're thinking is, to relate collision current and exposure to dose, there's a Q in that formula, and you do need CP to relate the two, right? So why don't I need CP in this case to relate the two? Well, it's actually a trick question. That's because this Q in this formula to calculate dose in gas is not the same as the Q, the other Q in exposure relating that to dose. So this Q in dose in gas is charge measured in the gas cavity. The other exposure Q is the total charge of one sign produced in the cavity. So it's a very tricky question. If you're studying this material, say for example a test, look out for this question. Look out for E. It's tricky. If you try and reason it, you may get it wrong. But remember that the Q's technically they have two different definitions in each case. Very tricky. Okay, so let's work through an example problem. So suppose you have a small air cavity ion chamber with copper walls. The thickness of the walls are equal to the max electron range, and it has a volume of 0.1 centimeters cubed and a density of 0.001293 grams per centimeter cubed. That's the density of air. And the charge measured is 7 times 10 to the negative 10 coulombs. Calculate the dose in air. So once again, we're just using that formula. And notice that we don't have the mass, right? But what we do have is the volume and the density. So we can rearrange this formula to calculate the mass. And that's what we've done here to get this measurement in grams. But we're going to want to remember that dose is calculated by joules per kilogram. So we're going to want to go ahead and convert the mass to kilograms. So now let's go ahead and plug in our units here. We have our charge measured. Plug that in. We have our mass now. And our constant, W over E, which is 33.97 joules per coulomb. We go ahead and cancel out the coulombs. We get 0.184 joules per kilogram, or gray, of course. Now moving on to part B. Calculate the dose to the copper wall using Bragg-Gray. And let's assume we have an incident 1 MeV photon. So there's our Bragg-Gray formula. Now, this is the catch. So we want to calculate the average mass collision stopping power, right? So we need to know the energy to grab the stopping power at, and I'll show you how to calculate it essentially. So what we're going to be using is this formula, and it starts off with T0, and this is T0 is equal to, it means the spectrum seen of charged particles with a mean starting energy of this amount of T0. It's the mean starting energy of electrons. And it's equal to the initial photon energy being 1 MeV photons, and then the mu Tr over mu. In our case, it's calculated from the medium, which is copper, mu Tr over mu of copper. So you're going to look these up in a table. So then we can go ahead and calculate T0. And now what you're going to do is take T0 divided by 2, and now you'll be able to find the average energy of the charged particle crossing the cavity. So this is the energy that you're going to pick your collision stopping powers for this ratio at this energy. So you're going to have to calculate for this energy and then flip to the tables, or use that website that I showed you to find the exact energy for stopping power, for collision stopping power. And you're going to put in the ratio of the two. So it's calculated from the medium. So let's go ahead and follow through. 1 MeV, there's our initial photon energy. This is our mu Tr over mu of copper. We get an answer of 0.443. And to get that average energy of charged particle crossing the cavity, we divide it by 2. So notice here that this first part of the Bragg-Gray formula, charge measured mass in W over E, we calculated in the part A. We got an answer of 0.184, so this is the same thing. We can plug in that value, right? So now all we need is this ratio. The average mass collision stopping power of W, which is the copper walls in this case, over gas, which is air in this case for an ion chamber. And we plug in our values, calculate. The answer is 0.1378 gray. Okay, so moving on to the next cavity theory formula, Spencer-Haddix. So what is the Spencer-Haddix formula? Q over M, W over E, which is the same, but in this case we're using the restricted stopping power. Part B, what's the difference between Bragg-Gray and Spencer-Haddix formula? It uses the restricted stopping power. The definition is it's the fraction of stopping power excluding all knock-on collisions with an energy transfer greater than delta. So for C, define delta and what's the value of it? It's typical value. Delta is the cutoff energy, or the energy of the electron that can just cross the cavity. Typical value is 10 kiloelectron volts. For D, what are the conditions for Spencer-Haddix theory? Both of the Bragg-Gray assumptions. You do need charge particle equilibrium, absence of Bremsstrahlung radiation, and you need distributed, homogeneous, and monoenergetic electrons that are emitted. So for E, essentially we have this formula here for Spencer-Haddix. We have a formula for Bragg-Gray. The only difference is this restricted stopping power. So for E, we're going to kind of look at some different situations and see, the difference essentially between Spencer-Haddix and Bragg-Gray. How much of a difference is there in each situation? Let's go through them. So for E, does Bragg-Gray differ much from Spencer-Haddix with energy? So let's use this chart. So for carbon, look at the change in energies. This is 1.3 MeV. This is Spencer-Haddix area, Spencer-Haddix. And this is Bragg-Gray over here, highlighted. Let's compare. 1.003, 1.005, difference of 0.002. Let's compare it to a lower energy. Once again, a difference of 0.002. So not really. There's not really much change with energy between bright gray and Spencer Addicts. What about with the Z of the wall? Atomic number of the wall. So let's look at lead. You know, we just went over carbon. Let's check out lead. 1.940 to 1.730. Yeah, quite a difference. 2.030, 1.876. Quite a difference. So yeah, there definitely is. So yeah, the two cavity theories definitely, they differ with the change in the Z of the wall, atomic number of the wall. What about with the change in delta, or cutoff energy? So highlighted it in green. Let's look at the change in delta here. 1.001 to 1.005. Bright gray, 1.005. So not really. You know, there isn't really much change with change in delta. Okay, so moving on to the last cavity theory, and that is Berlin theory. So what is the formula? I'll work through part B too at the same time, because they share similarities. So A is what is the formula for Berlin theory. B is define each variable down to its most simplest form. Okay, so here we have the dose ratio. Now we have this new quantity called D. D essentially, it's a parameter that's based on cavity size, and this is the formula to calculate D. 1 minus e to the exponent negative b. We use this formula to calculate b. And L. L can be calculated by 4 times the volume over the surface area. And over BL. So this is how we calculate D, and we need to calculate B and L to get D. Tmax in this case, used to calculate B, is the maximum range of electron and gas. And then for this formula we still have this mean ratio of mass collision stopping power. And within this formula we now have the mean ratio of mass energy absorption coefficient within this formula. For C, what are Berlin theory's conditions? There are many conditions. The gas and medium are homogeneous photon field everywhere with no attenuation. Charge particle equilibrium in the medium and gas, or medium and cavity, that are further from interface than max electron range. And the electron fluence generated in W is the same as in G. Then the last condition, the electron fluence originating in the cavity builds up to equilibrium exponentially as a function of distance in the cavity. So the fluence of incoming electrons exponentially attenuated in cavity with the same coefficient. So that one sounds difficult. Now for D, suppose we have a small cavity case. Berlin theory reduces, the formula reduces. What does it reduce to? So for the small cavity, for small cavity, D goes to 1. So if I plug in 1 here, this stays. If I plug in 1 here, this eliminates because this equals 0. So I'm left with just this mean ratio of mass collision stopping power. And that's what Berlin goes to. For E, for a big cavity, what does Berlin theory reduce to? For big cavity, D goes to 0. So I put a 0 in for D. This stays. For 0, this goes. So we're left with just this term, which is the mean ratio of mass energy absorption coefficient. Okay, so let's perform some calculations with Berlin theory. Okay, so let's say we have a 1 millimeter layer of water in between 2 equilibrium layers of Teflon irradiated by 2 MeV photons. Let's use Berlin theory to calculate the dose to the water if the collision in adjacent Teflon is 10 gray. And assume that all the conditions are fine and acceptable for the scenario. So here's the Berlin theory. I went ahead and gave the, this is the mu e n over rho. This is the average, so you can use these. This is for water, and this is for Teflon. So we're going to plug it in for there. Here are our formulas. I just put it along the side to keep it as a reminder. These, of course, should all be memorized. So let's start calculating T0. I plug in the initial photon energy, 2 MeV. I plug in, I found the mu TR over mu within the tables. And this is going to be for water. So I plug that in, I get an answer of 1.063 MeV. And then I can divide it by 2 to calculate T-bar. Now, since we now have the average energy of electron crossing the cavity, I can look up the mass collision stopping power ratio of H2O over Teflon in the tables or through that website, which is better, more accurate. And I looked up H2O and Teflon, and this is what I got. Now, what we have to find now is this B quantity, right? Because we're going to use it to calculate D. And to do that, we need to find what Tmax is, and we need to sub it in. Now, within ADDX page 185, table 8.5, there's a table for finding Tmax. And this is what it shows. Tmax over RCSDA range equals 0.95. I rearrange. And then what you do is you plug in the value for RCSDA, once again for tables, for water using the T0 energy. It specifies in the tables using the T0 energy. So I found the RCSDA range from a table, I plug it in, and I divide by the density of water, which is 1 gram per centimeter cubed, and I get a value of 0.415 centimeters. Notice the units. So now I have Tmax. I can solve for B. So I plug in Tmax into that formula. I take the ln of 0.04, and then I bring over 0.415, and I get 3.22, which is the ln of 0.04 divided by 0.415, and I get an answer for B of 7.76 centimeters to the negative 1. So now I need to calculate L for a formula for B, or for D, sorry. Okay, now there's a statement on page 252 of ADDX that says for a flat plate of infinite extent of our medium, you can use for L, instead of the 4 times the volume over the surface area, you can just use L is equal to 2 times the thickness of the inner cavity. So in this case, that's what we have. We have 2 Teflon layers that we're approximating as infinite extent with water in between them. So we can use this formula, which is very easy to use. So I plug in our, this is the distance of a layer of water, which is 0.1 centimeters. I get an answer for L of 0.2 centimeters. So now we can plug in B and L and calculate D. We get an answer of, notice the units, of course, 0.2 centimeters for L, and centimeters to the negative 1 for B. So they everything works out. So now we have all our quantities, and we can sub in all the values for Berlin theory, the calculation. So that's what I've done here. I work it out to get an answer of 1.18. This is D water over D Teflon. is equal to 1.18. But in our calculation, we're looking at equilibrium layers. And for our calculation, the collision kerma was given. It's equilibrium, so we can say it's approximate of a dose is 10 gray. So I can go ahead and plug in 10 gray for the DW, which is the medium or Teflon, and I get a final answer of dose in water, which is the cavity in this case, of 11.8 gray. Okay, now actually I'm moving on to problem 7. Essentially what I've done is I've taken the same problem, only instead of the scenario before where we had layers instead of layers, we're going to go ahead and assume it's a sphere of water instead. So I'll show you how to calculate L with the 4V over S, which is the 4 times the volume over surface area. So these quantities all stay the same. They're all the same as in the prior question. So I can kind of fly through them. Yep, yep. Okay, so here we are. So we just calculated B. We're going to put it in for D, but now we need L, right? So L is equal to 4 times the volume over the surface area. Our case, we have a sphere of water with a radius of 1 millimeter. So the volume for a sphere is 4 over 3 pi r cubed. The surface area for a sphere is 4 pi r squared. Notice that I can cancel out a lot of measurements. Cancel out the 4, cancel out the pi. 1 r on top, cancel out r squared. I'm left with 4 over 3 r. I can plug in our radius of 1 millimeter or 0.1 centimeters, and I get our final answer of 0.13 centimeters. I can go ahead and so let's go ahead and substitute in a value for L and B for D, and we get an answer of 0.63. And similarly, we can plug in the values and calculate the ratio of dg in our case, which is a sphere of water, over surrounded by Teflon, which is dw. We get 1.075. And similarly, we're going to say it's all the equilibrium. We're going to say it's approximation for CPE. So we can use this collision kerma of 10 gray and get a final answer for the dose in water of 10.75 gray. Okay. So for problem 8, we're going to look at a calculation that involves before we were looking at just the cavity in the medium or cavity in a wall. In problem 8, we're going to look at a calculation that involves a medium X, a wall W, in the cavity G. So for part A first, write down what the formula for Berlin theory would look like if you're incorporating the cavity, the wall, and the medium. So the formula changes. So this is essentially what it'll look like. It tacks on that extra mu n over rho of wall over medium. Whereas this mu n over rho is cavity or wall. Now let's perform a calculation for B. Water has a Z over A, which is atomic number over atomic mass, of 3.343. And polystyrene has a Z over A of 3.328. So very close, essentially. For cobalt-60, calculate the D cavity over D wall, which is the dose. For cavity of water, so the cavity is water, surrounded by a polystyrene capsule, within a medium of water. So water is the medium, polystyrene capsule, and water is the cavity. And we're going to do it for the small cavity and large cavity limit. So if you remember, for small cavity, D goes to 1. Substitute 1 in. So this disappears, and I'm left with just this quantity. And I went ahead and gathered the values, because it's just going through a table or or searching online for the ratios. So you can go ahead and plug it in. So for small cavity, we get an answer of 0.994, which is pretty close to 1 for the similar Z over A's. But let's look at large cavity limit. If you remember, for large cavity, the D goes to 0. So I can plug in 0 here. Now, okay, 0, when I plug in 0 here, this eliminates. I plug in 0 here, I'm left with mu E n over rho, cavity over wall, and mu E n over rho, wall over medium. So in this case, the walls can cancel out, and I'm left with just the cavity over the medium. That's what we have here. So if you remember from our example, the cavity is water, wall is polystyrene, the medium is water. So I'm taking the mu E n over rho of water over water. So the answer is 1. So what's great about this example is that it shows for a large cavity, when you match the cavity to the medium, you match it, they're the same material. The dose measured in each one is the same. It's equal to 1. Yeah. So essentially, with a lot of these questions, the one thing you have to watch out for is obviously you have to memorize all the formulas, you have to memorize all the terms, but in many instances, you have to be very careful when you're just working through the example problem itself. Like even, if you don't memorize this formula appropriately, you mix one of these terms, you get the entire question wrong. Especially any of the Berlin theory calculations. The Bragg-Ray and Spencer attics are very much just just memorize the formulas, plug and chug. The Berlin theory, long calculations, and you can forget a particular term, or just miscalculate one small thing, and you get the whole question wrong. So be very careful with that. Other than that, I think I put together an excellent video and lecture going through the different cavity theories in only 8 problems. And I think that's it for this video. Thank you very much. Thank you very much for viewing, and that's all. Bye.